kinematics deals with object motion. And so what we talk about when we discuss kinematics in maths methods is the position, velocity, and acceleration of a particle. So in maths methods, the particle can only move in a straight line, which is different from real life because particles generally can move in any direction they want, but it complicates the maths for our subject anyway. So if you want to imagine how an object can move in maths methods, what I want you to do, this is what I usually would do in class, is I, with masking tape, draw a straight line or connect a straight line between 2 points in front of the board. And if you imagine me teaching at the board, be doing my thing here, you know, drawing graphs and all of that sort of stuff, that the only way I can move is actually left or right along this line in front of the board. So if any of you ask for help and you say, can you come over here and help me? I say, no, I can't, because I'm only allowed to move left or right or in a straight line. Okay, so that's how the object motion works. And it just makes the maths a little easier for our subject. It does get more complicated when you look at vectors and things like that, but if you're only doing maths methods, this is the only way a particle is going to move. Okay, so what we do is we imagine that movement happening from a fixed point O on a line. So imagine that is O, the origin here. This is where I basically go, all right, guys, I'm starting my class now, and I start in this point here, and then I start moving left or right along the line, you know, demonstrating whatever I'm demonstrating. Okay. So by convention, movement to the right of the origin is considered positive. So if I'm starting at the origin and moving in this direction here to the right, we say that that's a positive. Okay, so I could say that my position would be 2 meters to the right of the origin if I was here. If I then moved across to this point here and was teaching at this point here, I could say 2 to the left or -2. Right, so if x equals 3, okay, if this x value equals 3 here, then the particle's position is 3 units to the right of the origin. If x, in this case, was here, and x was equal to 1, we would say that it is 1 unit to the left of the origin, or x is equal to -1. So sometimes what we can do is we can actually have a rule that enables the position at any instant in time to be calculated. Okay? So in this case, we view x as being a function of t. That is, the position, or this value x, is a function of the point in time. Okay? And the example I tend to use is, imagine you guys find that in every single lesson, you sort of notice that, wow, like he is in exactly the same spot, in exactly the same point, or at exactly the same point in each lesson. All right, so you know that at the 3-minute mark, I'll be exactly at this point on the board. Or at the 7-minute mark of the lesson, I'll be at this point on the board. And what you guys are able to do is actually develop some sort of a function that shows where I'm going to be at the board or relative to the origin at any given point in time. So that's exactly what this graph represents, this x of t versus t. What we basically do is grab this position axis, place it as a y-axis, and then put that against the time. All right, so what we've got in this graph here is we can tell that at time 1, the object is here, okay, or the particle is here, 4 units to the right of the origin, okay? At time 0, the particle is at the origin, etc., etc. So here's an example. A particle moves in a straight line so that its position x, and that's important, so we've got straight line motion, so methods applies, or our mathematics applies, so that its position x centimeters relative to the origin at time t seconds is given by this rule. So find the initial position of the particle. So that's saying, what is its position at time 0? T equals 0. And what we know is that x of 0 equals 6. And we can interpret that in kinematics as 6 centimeters to the right of the origin. All right, what about its position at t equals 4? So it's going, basically, where are you at time 4? So we're going to go x of 4 equals 16, take away 28 plus 6. 12, negative 12, negative 6. So our answer is negative 6, and we can have a negative position, and we just need to interpret that in the context of the maths that we're doing. That's 6 centimetres to the left of the origin. All right, so that negative 6 is okay, and we just interpret that as 6 centimetres to the left of the origin, as opposed to the positive, which is to the right. Remember, 0 means we're at the origin itself. All right, so what we've got here is some terminology. So we call this distance or displacement, and they're not the same thing. Okay, so the displacement of a particle is the overall change in position of the particle. So consider a particle moving from the origin to point P and then to Q. So basically it started at the origin, moved over to here, and then moved down here. Again, this would be a case of, if we imagine it, me up at the board, okay, and what I do, start at the origin, move over to this point here, and I'm pointing out something on the board here, then I move back this way and end up over here where I'm pointing at something on the board this way. Okay, so when we talk about displacement, it's the overall change in position of the particle, and all we consider is where we started and where we've finished. In this case, the displacement of the particle is negative 2. Okay, and all that means is I'm 2 centimetres to the left of where I started. Okay, well, I'm talking about I, myself here, but 2 centimetres to the left of where the particle started. Okay, so it started here, moved all the way along here, and then got back to this point here. So we can have a negative displacement, and remember, we just interpret the negative as to the left of, and we can have a positive displacement that is to the right of. All right, what is the distance travelled by the particle? So distance is always positive. Okay, we can never have a negative distance. And the way to think about that, if you say, what's the distance from here to the nearest cafe, it'll always be positive. If you think about it, you can never, in your life, reflect on when you've told someone a negative distance. It's never happened. In fact, in the movie Ferris Bueller's Day Off, they tried to run the K's off the Ferrari backwards or in reverse by reversing the car, but it just doesn't work. When you reverse the car, it actually adds kilometres to the car in theory. Anyway, I can't remember what exactly happened in the movie, but I just remember it didn't work. So the distance is always positive. All right, so the distance, let's calculate it. So particle moves 5 to the right, 5 back to the origin, and then another 2 more. Now, because it's the distance of 2, we quote that as positive 2. That's a distance covered, and it doesn't matter whether I've gone to the left or the right, it's just distance covered. So this is 12 centimetres. So the total distance covered is 12 centimetres. The displacement is negative 2, or 2 centimetres to the left of where the particle started. So important difference between the two things. Okay, so consider a particle moving according to this function here, which is pictured, I believe. Yep. What is the displacement of the particle over the first 5 seconds? All right, so what we need to do is consider where the particle starts and where the particle finishes. Okay, so we're going to go x of 0 equals 4, that's 1. X of, what was it, 5 seconds? X of 5, looks to be 6, let's just make sure. 5 to 3, 9, 6. All right, so it starts at 1 and it finishes at 6. Okay, so our displacement is going to be 5. Okay, displacement is 5 units, And the way we interpret that is 5 units to the right of where started. Okay, so if you think about it, starts there and finishes there. How far away from that is it? It's 5 units. And we notice that that's to the right. Okay, what's the distance covered by the particle? Now this is a totally different question, and what happens is the particle, what it does is it starts moving left, and it gets to this point here. Then what it does is it moves to the right and ends up at this point here. So we're considering all of the distance covered, not just a snapshot of what happens between here and here. It's actually this whole distance. Now we know that the turning point is 2, 3. So what it does is it moves from 3 rather. It moves from the start, which is at 1, all the way down to -3, which is a distance of 4. So the distance there to there is total of 4. And then what it does is it goes back and covers this distance here. So we're at -3 and we're going to go all the way to 6. That's a total distance of 6 and 3 is 9. So it's 13. Okay? And that one there, we just say the distance covered is 13 units. We don't know anything about left or right or which direction the motion has been. All we know is the particle has covered 13 units in total. Alrighty, so velocity and speed. Now, they're two different things. And here's two memes. If you actually look up memes on velocity versus speed, you'll find that there's a lot of people writing memes. So if you die in the same hospital in which you were born, your average velocity would be 0. Okay? So let's have a look at the difference between speed and velocity. So speed is the distance covered and the time it takes you to do that distance. All right, velocity, okay, is equal to, what did I write, S? Velocity is equal to the displacement over time. Okay, so what velocity is the rate of change of position with respect to time. What speed is the distance covered and the time it takes you to do that distance. All right, so let's look at the speed of this particular situation. So suppose you have a circular racetrack, has a circumference of 1,000 metres. Car drives around the track such that it takes 50 seconds for a lap. Okay, so we're going to go 100 over 50, because that's the distance and that's the time it took. 20 metres per second. Okay, so the speed is 20 metres per second. Okay, now what we're doing then is the car is going around this racetrack here, so we want to consider the displacement. Okay, so drives around and finishes there. And that basically means, if you think about it, if I look at the displacement of the car, that is the rate of change of position with respect to time, its position actually hasn't changed when it does a full lap. So it does the full lap and finishes there, which means its displacement is 0. And the time it took is 50 seconds. So velocity is 0 metres per second. All right, so important to note here, its speed, 20 metres per second, but its velocity, its rate of change of displacement with respect to time is 0. So that's what velocity is, the rate of change of position with respect to time, and we can work out the average velocity by simply looking at its change in position over that given time period. So it's the gradient formula. Okay, there's nothing fancy about that, so don't worry about that. It's just the gradient formula. It's y2 take y1 over x2 take x1, noting that the y-axis is the position axis with respect to time. Now, we can also calculate the instantaneous velocity via differentiation. So if we know the position with respect to time, the velocity function can be found by just finding the derivative of the position function. Let's try it out. So here's the graph of x of t. Okay, and what I want to know is the rate of change will either be positive, negative, or zero. So if v of t is that derivative greater than zero, so basically what we're considering here is the movement of the particle based on understanding its velocity. Okay, so what we want to know here is we can see here that the rate of change is positive. Okay, so let's find out where it's going to be positive. Okay, so we've got a positive rate of change all the way along here. Okay, so a positive rate of change or a positive gradient basically means that we can see that the particle is going to be moving in this direction here. So it's moving to the right. All right, so particle starts at negative, what looks to be about -6, and goes in this direction here. Okay, so it ends up at 20. That means it's starting to the left of the origin and moving to the right. Now, if we've got a negative gradient, like this one here, what that means, we can see from the graph that the particle is actually moving to the left. And if the particle has a zero gradient, then we say that this particle is stationary, or in the context of kinematics, we say changing direction. Right, so what's happening here? The particle is moving to the left, all right, and then it changes direction and moves to the right. Again, if you want to imagine me at the board, all right, what I'd be doing is initially this one here has me moving to the left, and then I get so far on to this point in the board that I decide, ooh, there's something over there that I want to point out, so I move back to the right again. So at this point here, I've changed direction. So what we say is this is a stationary point. Let's try it out on a function. So the particle moves in a straight line, so its position x relative to the start point at time t seconds, well, not the start point, but the origin at time t seconds is given by this rule. So find its initial velocity. So this is the position function. This is its position with respect to time. So the initial velocity can be found by looking at velocity at time 0. All right, so we're going to do x dash t to find the gradient. 2t takes 7, and we're going to say, what's your gradient at 0? And it says -7. All right, so the velocity is 7 centimeters per second. Right, that's what the velocity means. It's running at 7 centimeters per second, and I can also tell that because it's negative, it means the particle is moving to the left. All right, so initially the velocity is 7 meters per second, and it's moving to the left. So that negative sign is really interesting because it tells us something about the way the particle is moving. When does its velocity equal 0, and what is its position at this time? So I'm looking for a stationary point, so I can see that it's going to occur at around about 3.5. So that's when it's going to happen, is at around about 3.5. And its position is going to be somewhere at -6 or 6 units to the left of the origin. Okay, so I can see it graphically. Let's work it out mathematically. So when does the velocity equal 0? So we're going to find out when that happens by doing x dash 0 equals x dash t equals 0. So we're going to say to the gradient function or the velocity function, when are you 0? So we're going to go 2t take 7 equals 0. T is equal to 7 on 2. Right, so what that means is at 3.5 seconds. So when does its velocity equal 0? At 3.5 seconds. Okay, so now that we know that at time 3.5 seconds it has a 0 velocity, what we'll do now is get its position at that point in time. So that is going to be found by doing x of 7 on 2. So we're going to put that into the position function, and we get 49 on 4, take away 49 on 2 plus 6, 49 on 4, take away 98 on 4 plus 24 on 4, negative 49, 39, 29, 25, negative 25 on 4, which is negative 6 1/4. That makes sense. And so what that means is position is 6 1/4 centimetres to left of origin. Now, how do I know it's to the left? Because it's negative. All right, average velocity for the first 4 seconds. All right, so watch out for this because we aren't actually going to use the velocity function because we're not after the instantaneous velocity, we're after the average velocity. And the average velocity can be found by doing the rate of change of position with respect to time over the first 4 seconds. So all we'll do is we'll say average velocity equals x of 4 take away x of 0 over 4 take away 0, which is 4. Okay, so working out its position there, and divided by 4. Okay, so it's the first 4 seconds, so we can see that we're going to get a negative gradient over this time here. And let's just see, initially it was 6, and x of 4, let's see if I can do this in my head, 6, have I done x of 4 already? No. 16 take away 28 is negative. 28 take away 16, 4, 12, negative 6. So that's negative 12 over 4, which is negative 3. Okay, so the average velocity is 3 centimetres per second, right? That's its average velocity. And again, the negative of this means that I know it's moving to the left. Okay, it's moving left because it's negative. All right, so that is the interpretation of it. That is the velocity, centimetres per second, negative 3 centimetres per second. But the interpretation is 3 centimetres per second moving left. All right, the average speed over the first 4 seconds. Okay, so this is a different question. So this is speed equals the distance over time. Speed equals, don't know the distance covered, but I know it takes 4 seconds. Now we just need to work out the distance. Okay, so we know that the particle starts here, moves down to here, and then moves back to 4. All right, so the stationary point occurs there, so I know that the distance, so it starts here at x of 0, which is 6. So it goes to the origin. So that's a total of 6 units. Then it goes down to its stationary point, which we worked out occurs at 6 1/4. So the distance there is 6 1/4. And then it ends up at this point here, which we just worked out as 6. So it goes back another quarter. So it's going to be, distance covered is 6 plus 6 1/4 plus another quarter to go back. Okay, so that's going to be 12.5 over 4. That is, we can't really write it like that, so I'm just going to say that 12 and a half, 25 on 2, 25 on 8 meters per second, centimeters per second. All right, so again, speed is quoted as a positive value, okay, and it's a different measurement to its average velocity. So the average speed and average velocity do not yield the same results. Okay, we finally finish on acceleration. Okay, so acceleration is the rate of change of velocity with respect to time. So that is, we're looking how the velocity is changing. Okay, so the average acceleration is given by the change in velocity with respect to time. So this again is just the gradient formula. Okay, and we can also get the instantaneous velocity by getting the derivative of the velocity function. So the acceleration function is found by doing the derivative of velocity with respect to time, or the double derivative of the position with respect to time. Okay, so how does this work? Let's just see. So we've got x of t equals 2t. All right, so this is the position function. So I can see here that the particle is moving to the right. It starts at the origin here and then continues to move to the right. Now, because it's a linear function, I know that it's got a constant rate of change, that I can see here that the gradient is 2 throughout. Okay, so we say that this has got a constant velocity. And finally, if I get the derivative of the velocity function, so x dash t is equal to 2, that's my derivative of the rate of change function. If I derive this to get the double derivative, I can see that it's got zero acceleration, i.e. the particle is not accelerating. Okay, the rate of change of the velocity is 0. So it's moving, okay, but the velocity is not changing. It's constantly 2. Okay, so the particle, we say, is not accelerating. A few interesting points about acceleration. So the direction of motion, that is the way the particle is moving, and the acceleration don't need to be the same thing. All right, so the reason for that is a particle may have a positive velocity, that is moving right, but a negative acceleration, slowing down. So you can move to the right and slow down, and you're going to have to do that if you want to change direction. Okay? So if acceleration has the same sign as velocity, then the particle is speeding up. So if we find that you get a negative velocity and a negative acceleration, that means the particle is speeding up. And if it's a positive velocity and a positive acceleration, it means the particle is also speeding up. That's the way to think about it anyway. And if the sign is opposite, that means the particle is slowing down. Okay, and probably one of the hardest things that students find to grapple with is, although a particle may be instantaneously at rest, its acceleration at that instant need not be 0. Okay, so you can have a 0 velocity and a non-zero acceleration. And basically, if you think about it, all right, I'll use this example here. Got a ball in my hand and I throw the ball up in the air. What's going to happen to that ball is we can see the ball goes up into the air, and at this point here, okay, so the ball goes up into the air, and at this point here is where the ball decides that it's going to change direction and come back down again. Okay, and so what happens is that the ball goes up, okay, and at some point, depending on how hard I've thrown it up into the air, it will change direction, which we say has 0 velocity. So we've got 0 velocity at this point, okay? And though we note that we can have a non-zero acceleration, and the reason for that is that accelerating against us at any point in time is this thing here. It's negative 10, or as physics students might know, negative 9.8 meters per second. And that's gravity, okay? That's gravity just pushing us down at that rate. It's the reason why when you jump in the air that you actually come back down again, is because of gravity. So let's just try this out on an example. A car starts from rest and moves. Sorry about the bell there. A car starts from rest and moves a distance of s meters in t seconds, where this is the function. All right, so what is the initial acceleration and the acceleration when t equals 2? Okay, so what we'll do is, so this is the displacement function. So I'm going to say that this is let x of t equal that. Then I'm going to get my velocity function. And further to that, the initial acceleration and the acceleration at time t equals 2 is found by doing the double derivative. That's going to be t plus half. Let's see if I've done that right. Yeah, t plus a half. So x double dash 0 is a half. All right, so we say that that is, or the interpretation of that is half a meters per second. All right, so that's the rate of change of velocity with respect to time at that point. And at t equals 2, so we're going to go x double dash 2. We're going to say that that is, where am I putting it into? Is 2.5 meters per second. So the interpretation of that, it's the rate of change of velocity with respect to time is 2.5 meters per second.